Okay, today's lecture is about waves. Yeah. Waves. This new section about waves. So what is wave? So in physics, we know the notion of waves and particles. Okay, so it means that this display setting. Okay, you see whole slide there. Hello.
Yes, Pak.
Okay, so the waves means properties of matter. Matter has two properties. First is particle properties, and the second is wave properties. In Newton mechanics, we study the matter can be thought of as a particle. So it means we have a matter that dominant particle. Yeah? Particle dominant, okay? But in this case, we consider a matter can be thought of as a wave. Yeah? So the wave is a property, okay? Okay, what is particle? Well, particle, there is no standard definition about particle, but particle can be said as a concentration of matters that can transmit an energy. Well, it's not a standard definition, okay? Particle. You can say particle is a thing, properties of matter. What about waves? Waves is different from the particle. It has a broader distribution from energy in the space. Yeah? So it could propagate the energy through the medium or without medium, with or without a medium. Okay, it's not a medium. So in modern physics, we said that in macroscopic point of view, the matter has what we can say is dualism properties. Yeah? Dualism properties. These properties, this matter could be particle, has particle properties, and has wave properties. We call it matter waves. Okay? So somehow there is, in the sense that this matter in microscopic point of view, it has a duality between waves and the particle. Okay. So what is the type of the waves? Okay, so this is some example of waves. In general, these three, water wave, sounds, and stadium waves, these are mechanic waves. But this light is a wave, yeah, but it can be viewed, it can be thought of as electromagnetic field. It can be modeled as an electromagnetic field classically using Maxwell equation. So that's why we study about waves, because the Maxwell equation implies there is a waves that transmit without the medium called electromagnetic waves, and it can be modeled. The light can be modeled by electromagnetic waves. Okay, this water wave, okay, it means that this wave propagate through the water. So water moves up and down, okay? It transmit the energy. And also sound, for example, the medium is the air, okay? This sound propagates we are through the air, yeah, with fast and forward, fast forward, yeah. And then the stadium waves, you see that if you, well, like in GBK, Gelora Bung Karno, the stadium, you see that if there is a football match, yeah, some fanatic football match could make these stadium waves, okay? Some people standing and then some people sit down, yeah, and they are, well, yeah, okay, something like that. So there are three types of waves. This called mechanics wave that we have shown as we have discussed above. This is sound, water, and the other waves that propagate through medium. And we have electromagnetic field that can propagate without medium. Okay, this example, light, for example, radio waves and others, X-ray, gamma rays, also infrared, etc. And also we have matter waves in quantum mechanics. But in our lecture, elementary physics, we only study or discuss this first type, these mechanics waves, and then the electromagnetic waves. So this is type of the waves, yeah, according to its, what is it? Okay, this type of waves, according to the disturbance, yeah, relative disturbance with respect to the direction of the propagation of the waves, okay? So for example, this is sinusoidal waves, okay? We have oscillation direction, yeah, oscillation direction is in vertical, the oscillation direction. And then this from left to the right, this velocity here indicates that these waves propagates, yeah, from along this x-axis, okay? So this is called the transversal waves because its propagation, this oscillation direction is perpendicular to the direction of propagation, okay? And below the second picture, yeah, we have longitudinal waves. It means that this propagation, the oscillation direction is parallel to the direction of propagation of the waves, okay? So for example, we have, for example, gas here, and someone here move back and forward, yeah, back and forward. So we have this some interval which has very the density is big, yeah, very dense here, the interval, and then it's not really there. It's almost no matter here, okay? So this is called longitudinal waves. Is there any question for this lecture until now? Any question?
Yes, sir.
Okay, any question? No question, okay. So in general, this is very special case of waves, okay? Transversal waves and longitudinal waves, okay? In general, the waves could have transverse combined. Okay, so in general, the waves could be the combination of transversal waves and longitudinal waves. Okay, in general. Okay, and also its polarization direction. So this is already polarized. Yeah, for example, it's transversal because it's only along this x-axis. Okay, this polarization, this oscillation direction. Okay. Okay, let's continue. So this is some, well, some picture, some of longitudinal waves, for example, above. Yeah, you see that this is then the dance of medium, yeah, moves along. Yeah? Okay, in this first picture, and this is longitudinal. Sorry, this is transversal waves. Okay, so they propagate, and the oscillation or the vibration direction is perpendicular to this propagation direction. And in above, the vibration direction is parallel to this propagation direction. Okay, so this is another example of water waves, for example. You see that these 2 points here, the blue one, the blue dot here, blue dots, okay, they stay at their position, okay, they not move, okay, only this one moves, okay. So it shows that the wave phenomenon, it means that it propagates the energy, okay, along this line. This is water waves. This is another example of wave. Yeah, this is called Rayleigh type of waves. It's also the combination of longitudinal and transversal waves. It can be found in the solids, on the solids. Okay. Okay. So what about the properties of the waves? So in waves, we have this wavelength, okay? This wavelength lambda, okay? For example, it has the maximum value. So the 1 lambda, it means that we have this point, the maximum value, connect to maximum value, okay? Or we get, for example, a hill, yeah, this one, and the valley, okay? 1 hill, 1 valley. This is also 1 length, 1 lambda, okay? And also we have the amplitude, okay? The amplitude is the maximum vibration, yeah? The maximum value of vibration, yeah, at a point, okay? So this is, for example, this is the amplitudes, A. And then we have the period, okay? The period is the time that complete 1 lambda, okay? So for example, from this maximum value, on the top of the hill, we have this is on the top of the hill, so this is 1 period. Or 1 hill, 1 valley. We have 1 one period. Okay. Okay, the dimension of wavelength is wavelength, meter. Okay, and the period is second. So this is the waves. Yeah. For example, in the first picture, we have at t equals 0, there is no waves. And then at t equals capital T over 4, this is a quarter of the periods, we have a quarter of lambda, okay? And then we have a half of lambda, we have 3 over 4, 3/4 of lambda, and then at the end we have 1 lambda, okay? Which is the t here is equals to the periods. And v here, v is the speed of the propagation of the waves, okay? This v equals to this wavelength over the t, okay? Any question about this picture? No? Okay, let us continue. So in other words, we have the speed of the propagation speed of the waves. We have this v equals to lambda times f, where f, we call it a frequency, okay? Frequency and the units is hertz, okay? Per second, the number of the period per second. Any question about this? Okay, no question. Okay, let's move. This is, for example, a ship, yeah? Ship in the ocean. Okay, we have the maximum value of, the distance between the maximum value of the waves is 20 meters. And the speed of the wave is 5 meters per second. How long the delta t needed for the ship move from the top to the valley, to the top of the hill, from the top of the hill to the bottom of this valley of the waves. Okay, you see that the key point is that from the top of the hill to the bottom of the valley, how many lambda? Hello, hello? How many lambda? Let's say, Reno. Hello, Reno. Hello?
Yes, sir.
Okay. How many lambda from the top of the hill to the bottom of the valley?
I think it's half, sir.
Yeah, very good.
Okay, sir.
Okay, yeah. It's half lambda, okay? So we have this v equal lambda over t. This t is lambda over v, okay? This lambda 20 and v equals 5 meters per second. So we have the one period is 4 seconds, okay? So because we have half lambda, it should be the time from the top of the hill and to the bottom of the valley, it's delta t is half of the period, okay? So we get 2 seconds, okay? Any question? Any question? Okay, no question, good. So this, for example, for sounds, yeah? The speed of sound in the air is around 300 meters per second, and the speed of light in the air is around 300 million meter per second. So, for example, if we have the wavelength of the sound, so if we have both the wavelength of the sound and the wavelength of the light have the same wavelength, the wavelength is 3 meters. What is the ratio between the frequency of the light compared to the frequency of the sound? Okay. So we get that because F equals to V over lambda. This V is the speed of light or the speed of the sounds in the air. So we get that the ratio between frequency of the light and the sound is equals to the speed of light over the speed of the sound. Okay, it's around 1 million. So it means that if you see the thunder, you know, the god of thunder, Thor. Yeah. Okay. So if you see the thunder, we see the light first, okay, and then the sound of the thunder. We will hear the sound of thunder later, a couple seconds maybe, yeah, after that. So that's so because the speed of light is much greater than the speed of the sound. Okay. So the comparison, the ratio of F light over F sound is 1 million. What does it mean? Okay. So for the sound, this F here is around 100 hertz. Okay, this is the sound which cannot be heard. This is low human, yeah, below the frequency that below human ear. Okay, we cannot hear this sound, this type of sounds. Okay, low from human, the standard normal human, the ear. Okay, and for the light, we have this frequency is 100 megahertz. This is the radio wavelength, okay? This FM, radio FM, frequency modulation. So this is, for example, the microwave, you know the microwave. So the waves that produced by this device called microwave is a microwave. This microwave, the wavelength of the microwave is around 3 centimeters. What is the frequency produced by these waves that cause the water molecule in your food vibrate? What is your answer? So we get that this V is equal lambda times F. Okay, this F equal V over lambda. So we get this the frequency for 3 centimeter wavelength. Yeah, we get this 10 gigahertz, 10 to the 10 hertz or 10 gigahertz. Okay, it means that the frequency, the water that the vibration frequency of the water, it's 10 to the 10 cycles per second. Okay, it's very fast, this vibration. Okay, so you see that if you try to warm your food using the microwave, for example, you set for 1 minute, for example, the energy of this microwave in the device is focused on at the center of the food. That's why if you use the microwave, the center of the foods becomes hotter than the other part of your food, because it's very focused on the in the microwave. Is some of you already cook, for example, eggs in microwave? Eggs with the skin, yeah? Not skin. Or the shell of the egg, yeah? Using, have you cooked the eggs with its shell? Hello? Anyone? Anyone? What happened? Bagas, Irfan Nuriski.
Yeah,
Hello?
Pak. Yes, Pak.
Yeah, what happened if we cook the eggs, yeah? The eggs is not cooked egg, but if you buy eggs from store, for example, and directly you put cook it using microwave, what happened?
It would just dry up.
Dry up.
It would just get dry.
Okay. Muhammad Faza.
Halo, sir.
Faza Abel, yeah.
Aku dengerin. Okay.
What happened if you cook the eggs, yeah, with its shell in the microwave?
Perhaps it would also dry up, sir. I haven't tried it.
Okay.
So I
okay.
can't really tell. Sorry.
Okay. Reno. Hello?
Yes, sir.
Yeah, what happened?
I'm not sure, sir.
You're not sure, okay. Okay, raise your hand. Which one of you at your house who do not have microwave? Raise your hand. Do you, all of you have a microwave, yeah?
Yes, sir. I'm sure everyone here has a microwave.
No, sir. I don't have a microwave.
Okay.
Oh, never mind then.
You have to try cook the raw eggs with its shell directly to microwave. What happened? Okay.
Sir, with the shell or without the shell?
With the shell.
Would it explode?
Sorry?
Would it explode?
Yeah, it would explode. It blows up. Yeah, I tried this when with my wife, of course, when we were in the Italy, yeah? Because I was a PhD student who was traveling to Italy as a conference. And when we tried to cook the eggs directly from the store, it blows up. So you have to clean up this mess. Okay. That's an interesting experience, I think. You blow up the eggs in the Italy. Okay. Any question? Any question? Okay, no question.
Sir?
Yes?
I have a question. Why the egg would explode, sir? Why does it explode?
Okay, because you see that the energy of microwave that produced in the device microwave, focus on that at the center, okay? At the center. So, because this X as blow up, okay? It should be there is, well, this from, there is a pressure, okay? Pressure, the energy that focus at the center gives, because the X becomes, well, boiled, boiled, and it has a pressure outside, okay? It's greater than you boiled it in the water, okay? So it has the pressure, so because this pressure, it's very big, so the shell of the eggs cannot, what is this in English? Okay, the cell of the egg cannot hold it, cannot hold this pressure, so that's why it's blow up.
Yeah, I see, sir. Thank you.
Yeah. Well, you should try this, okay? It's fun, okay? We don't know yet.
But
We didn't know yet
to
until we tried, okay? Okay. So I try this with my wife, okay, when we cook, because we don't know, because we don't know, so it blows, okay? Okay. So if we cook the water, for example, at the microwave, okay, it becomes warmer and then hot, okay? So it means that the water molecule absorb the energy of the microwave. So in order to rise its temperature, okay? So this is the graphic, the absorption coefficient of the water as the function of the energy, okay? So this one, this F here, we have this F 10 gigahertz, we have this one, okay? So the absorption coefficient is quite big here. But the water usually has an anomaly, okay? This anomaly occurs or happen at the visible range, around this 10 to the 14 hertz. Somehow the absorption of the visible light, visible electromagnetic waves, the absorption become decreasing, extremely decreasing, 10 to the, what is it? Decreasing to this value, okay? It's very low, almost zero, okay? And then after we rise the frequency, they become also the absorption become extremely increasing, okay? This is the anomaly of water, the anomaly of water. This is called water hole. Yeah. Okay, then we move to wave function. In particular, in our lecture in elementary physics, we consider the wave function to be sinusoidal function, okay? It can be written as this, for example, y as a function of x over comma t equals to ym sinus kx minus omega t. Okay? Can you guess which direction is the vibration or the oscillation direction in this case? Hello? Let's see. Vanes Livaldo. Hello, Panes.
Hello.
Yeah. Which one is the direction of vibration? Vibration direction of this wave for this function?
To the right.
Just a moment. Yes, the vibration direction.
Up and down.
Which axis?
The axis.
Nicholas Ariandra. What is your answer?
Is it to the y-axis in the negative direction?
Yeah. Okay, good. If we consider such a function, this y equals y as a function of x, comma t, it means that the vibration direction is along this y-axis, okay? This x here indicates its propagation direction. So the wave propagates along the x-axis, okay? Okay, Ym, we call it this amplitude. Kx minus omega t, we call it phase. Okay? This k, we call it wave number. This k here is equal to 2 pi over lambda. Okay? So if delta x equal lambda, so the phase change to increase by 2 pi. Okay. Omega is angular frequency. Okay. 2 pi is in the radians. Okay. Is equivalent to 36 degrees, 360 degrees. Okay. It means that one period. Okay. One period means we have phase added by 2 pi. So this is the example, for example. Example. Yeah. Example. So write the wave function, sinusoidal transversal. The wave function, which is sinusoidal, it is transversal wave, propagate along the road, along the string, yeah, the string, in the direction of y plus, yeah, with the number of the wave is 60 centimeter to minus 1. The period is 0.2 second, and the amplitude is 3 millimeter. Take the z as the transversal direction. Okay, this is the transversal waves. So you see that if we indicate this k is 60 centimeter, 60 per centimeter, we have t, capital T, is the period 0.2 second. So because the z is the transversal direction, so we should have Zn is 3 millimeter. Okay, so the function of this wave is z as a function of y, comma t. Okay, the propagation is along to plus y. Okay, so it should be, this is ky minus omega t. Okay, because we have this omega is 10 pi hertz, so we can write the wave function as this one. Z y comma t is 3 millimeter sinus 60y minus 10 pi t. Any question about this problem? Any question? Any question? No. Okay. So the problem B is that you have to compute the speed of the vibration, the maximum speed of vibration, the speed of vibration, the maximum speed of vibration in a point at the string. So the speed of vibration or the speed of the oscillation, we have this definition, okay? UZ is the derivative, the partial derivative with respect to the t, okay? So we have this minus omega Zm cos ky omega t. So we get this one, okay? So the maximum, so the maximum value of this, the maximum value of speed, the speed of the oscillation, the maximum value of the speed of the oscillation is this one, okay? Uz equal omega Zm, okay? We have omega here and we get also Zm, okay? We get this around 94 millimeter per square. Any question about this problem, this question B? Any question? Okay, I just asked the committee of the examination. So the examination one on Saturday will be, we will use the model, yeah. So, okay, should be no problem. No question? Hello? Any question? Okay, let us continue. How about this one? Can you write down your answer and then upload it at the Teams? Yeah? Okay, 10 minutes. Let's say this is quiz. Yeah? Okay. Okay. Okay, let us continue. So we get the sinusoidal y Okay. Y is x comma t equals ym sinus kx omega t. So you could also, because there is no statement, the oscillation direction of the sinusoidal, so you can also write this y or z. Okay. Okay. So if you write y di sini here, so we get this ym sinus kx omega t. So because it is not also state the direction of the propagation, you could also write, for example, this kz, x replaced by z, you could also write. Okay. So let me write this y as a function of x and t. We get this ym sinus kx minus omega t. So the frequency is 500 hertz. The velocity, the speed of the wave is 350. This is not millimeter, yeah, meter per second. Sorry, there is a mistake here. So the phase here, we get this k is 2 pi over lambda, and the speed is omega over k. This is a frequency, okay? So how long the distance between 2 points in which they have phase difference pi over 3 radian. Okay, this is the phase difference. So this is the phase, this is phase difference. So usually if we took the phase difference, this is should be delta x minus 2 pi f delta t, because we have here only the spatial distance, so we have to set that this delta t equals to 0. Okay. So at the same time, it means that the phase difference between 2 points at the spatial distance at the same time. So A means here at the same time. Okay. So we get that this equals to 0.117 meter. The distance between the point. Okay. B, the phase difference between. Okay. So A is the phase difference. So the A here the phase distance at the same time. Okay. But B here, the phase difference at the same point in space. Okay, so this delta x, this the problems B, delta phi here, okay, there is the delta x equals to 0. The delta x equals to 0, so we have only 2 pi f delta t. Okay, we have this time difference 1 millisecond. Okay, this millisecond, it means that 10 to the minus 3 seconds. So we get delta phi here is the p radian. Okay, is there any question about this?
No, sir.
No, okay. Okay, good. So this is in general, the waves is not the function of sinusoidal, but we could express it in terms of sinusoidal. This is, we call it Fourier series, okay? This is, for example, where these the actual waves on the left and the right is the Fourier series, okay? So the left is, we get the state function, okay, the state function. We could approximate it by the Fourier series, okay? So this is the Fourier composition, and this is the result. And this is for another waves, okay? This is, for example, the linear, not linear, yeah. For example, this y equal x, for example, or y equals to minus x, yeah, in the particular direction, in the particular direction. And then this is the sin function. Sin means sin x per x. We call it sin. S-E-N-C, sin x. Sin x means sinus x per x. So let's say the speed of the waves. So how fast is the waves propagate? We get that this phase kx minus omega t is constant. Okay. This v here, the propagation speed, this v defined as dx over dt. Okay. So we get that this is equal to omega over k. Okay. So if the propagation from left to the right, so v is greater than 0. But if the propagation of the wave from the right to the left, we get the velocity of the, sorry, not the speed, the velocity of the wave is negative. So the speed of wave is a constant, which depends on the medium. Yeah. On the medium, not amplitudes, or wavelength or the period. Okay. So this is, for example, for transversal wave on the string. Yeah, we have mu here is the mass density of the string. Tau is the force here. Yeah, the string tension, this tau here, string tension or force. Okay. So, for example, is on the string, you take this the vibration here. Okay. So at this point, at the maximum point, we could, around this maximum point, we could approximate these pulse here by the circle with radius capital R. This mu here, as we see, that is the mass density of the string. This F here is the force or tension of the string. So this is what it's look like, okay? The net usually, because the horizontal component will cancel to each other, so we have only the vertical components, okay? Because theta is very small, so we get the sin theta is approximately 2 theta, while cos theta approximately equals 1. Okay. So this m here, it should be r times 2 theta, which is the angle here, r times 2 theta times mu, okay? Okay, because we have this circular motion, from circular motion we get that at the infinitesimal level, this force here equals to this mv r squared over r. Then we get this F equals to mu times V squared. And then we get this V here, square root of F over mu. Okay? This V here depends on the properties of the string, the matter. So mu is the mass density of the string. Okay? Is there any question to this point? I will summarize today's lecture in Bahasa before we will end this lecture. Is there any one of you have a question? Ada pertanyaan? Okay, let's summarize the lecture in Bahasa. Oke, jadi untuk siang ini kita kuliah tentang gelombang. Ya. Jadi gelombang itu adalah sifat sebuah benda ya. Benar dikatakan ya bersifat gelombang atau bersifat partikel. Jadi partikel itu tidak ada definisi yang standar lah ya. Jadi definisinya itu biasanya kita cuma mengambil terkait dengan partikel itu konsentrasi materi gitu ya dalam batasan ruang tertentu. Dan dia dapat mentransmisikan energi. Ini partikel. Sedangkan gelombang itu distribusinya itu lebih lebar gitu ya. Kalau partikel itu hanya terkonsentrasi lokal, kalau gelombang itu bisa lebar. Jadi contohnya tadi seperti kita ambil gelombang sinusoidal, panjangnya berapa gelombang sinusoidal? Anda ada yang tahu nggak panjangnya berapa? Melvin. Panjangnya berapa gelombang sinusoidal yang tadi?
Halo Pak.
Panjang dari gelombang sinusoidal, panjangnya berapa itu? Bukan panjang gelombang ya. Panjang gelombang sinusoidal, panjang gelombang dengan beda ya, panjang gelombang dengan panjangnya gelombang sinusoidal. Berapa panjangnya itu? Anda menggambar sinusoidal itu biasanya dari mana ke mana? Melvin, tadi mana sih Melvin? Tidur
Halo
wajahnya.
Pak. Halo Pak.
Ya. Gimana jawaban kamu apa? Kira-kira.
Panjang sinusoidal ya Pak?
Ya, panjang gelombang sinusoidal.
Satu dari peak ke peak bukan Pak?
Oh itu satu panjang gelombang. Kalau ini panjang gelombang sinusoidal, beda lagi. Kalau Anda menggambar sinusoidal itu kira-kira ada dari mana ke mana?
Kalau sinusoidal biasanya mulai dari x-axis bukan Pak?
Ya ambil x-axis lah misalkan. Dari mana ke mana?
Plus 1 min 1 Pak. Jadi naik 1 turun ke min 1 gitu Pak.
Yang tadi yang belum siapa ya? Selin.
Halo Pak.
Ya, panjang gelombang sinusoidal berapa? Panjangnya gelombang sinusoidal. Bukan panjang gelombang, bukan lambda.
Yang Y itu bukan sih Pak?
Yang di sumbu X. Bukan Y-nya, kalau Y-nya kan arah getaran.
Yang KX min omega T itu Pak.
Ya. Panjangnya berapa itu? Panjangnya gelombang sinusoidal. Oke, Anda menggambar sinusoidal itu biasanya dari mana ke mana? Ada yang bisa jawab nggak?
Panjangnya 2 pi bukan Pak?
Misalkan Anda gambar 0 sampai 2 pi. Setelah 2 pi ada nggak?
Nggak ada Pak.
Hah? Ada dong gitu loh. Kan ada yang kelipatan 2 np. Kalau ada kelipatan 2 np ya berarti di n sama dengan 1-nya ada. N sama dengan 2. Ada. Kalau sebelum 0 ada nggak? Ada juga. Berarti panjang gelombang sinusoidal itu dari tahingga sampai plus tahingga. Tapi ujung-ujungnya 0 ya. Ujung-ujungnya 0. Ya, itu Anda pikirkan lah ya sendiri. Oke, jadi gelombang itu dia distribusinya bisa tadi dari min tahingga sampai plus tahingga. Dia mengisi ruang gitu ya, dan dia merupakan penjalaran, gangguan yang menjalar ya, atau disturbance ya, propagating disturbance. Jadi bukan medium ya sifatnya. Oke, kemudian di perkembangan terakhir mekanika kuantum yang disebut namanya gelombang materi. Jadi secara mikroskopik sebenarnya benda-benda itu bisa istilahnya bersifat dua, bisa gelombang, bisa partikel, yang disebut namanya dualisme gelombang partikel. Jadi kita nggak bisa nyebut itu sebagai partikel karena dia bisa sebagai gelombang. Jadi disebutnya matter wave, materi gelombang. Nah, itu ada sifat dualisme di sini, dualitas. Kemudian tipe gelombang yaitu ada contoh-contohnya, ini contoh gelombang air yang bergerak naik turun, kemudian bunyi, bergerak maju mundur, kemudian gelombang stadium ya yang orang bergerak tuh di lapangan bola ketika main, misalkan ada klubnya menang, itu orang-orang ada yang apa istilahnya bergantian berdiri, duduk, berdiri, duduk itu seperti gelombang kan gitu. Kemudian ada gelombang cahaya gitu. Nah, 3 gelombang yang ini, yang air, bunyi, dan stadium itu gelombang mekanik. Dan biasanya dia menjalar melalui medium. Sedangkan gelombang cahaya tidak. Oke. Nah, ini tipe gelombang, ada gelombang mekanik, seperti bunyi, air, dan yang lainnya. Kemudian gelombang termagnetik, cahaya, dan tidak perlu medium. Kalau yang mekanik dia perlu medium. Sedangkan gelombang materi itu tidak perlu harus medium juga. Nah, ini contohnya sinusoidal ya. Jadi menurut apa istilahnya arah gangguan, arah getarnya gitu ya, relatif terhadap arah propagasi. Jadi kalau untuk gelombang transversal, arah propagasinya ini Anda lihat di sini itu dia arah getarnya ke sumbu Y, arah propagasinya ke sumbu X. Itu kan tegak lurus ya. Jadi mana itu? Kemudian yang kedua itu adalah gelombang longitudinal yang arah perpindahan mediumnya itu searah dengan atau paralel dengan arah jalan gelombang. Ini contohnya ini. Kalau kita gerakan fast and forward gitu ya. Jadi bergerak ke depan, belakang gitu ya. Itu nanti yang didapatkan nih ada satu yang lebih padat, satu yang lebih renggang gitu. Lebih kosong. Gitu. Nah, ini tuh ada jarak di sini. Di jarak ini biasanya di sini antara misalkan di sini puncak dengan puncak ini satu gelombang dan kecepatan propagasinya itu ke arah sana. Kemudian ini contoh gelombang longitudinal ya, yang Anda lihat kan digerakin kan ya. Kemudian gelombang transversal. Ini adalah contoh gelombang Rayleigh ya, di mana ini merupakan gabungan antara longitudinal dengan transversal. Oke. Tadi ini apa ini gelombang, ini Rayleigh itu. Oke, nah ini sifat-sifat gelombang itu ada panjang gelombang, lambda, ada amplitude, ada periode. Jadi lambda itu jarak antara puncak bukit, puncak lah, atau dia satu bukit, satu lembah. Itu panjang gelombang. Kemudian ada periode, itu adalah yang disebut T besar, itu adalah yang oscilasinya sudah lengkap ya, itu satu gelombang. Ini contohnya misalkan yang atas itu masih belum ada gelombang, kemudian ada 1/4, setengah, 3/4 dan sampai satu gelombangnya. Gitu. Nah, jadi bisa didapatkan bahwa V di sini itu adalah lambda per T besar atau lambda kali F. Dan satuannya itu adalah untuk frekuensi, gitu ya, di mana F itu adalah frekuensi dan satuannya itu adalah per detik atau hertz. Nah, ini contoh misalkan sebuah kapal di dalam di atas lautan, dia bergerak ya, gelombangnya itu misalkan 20 meter itu termasuk tinggi ya. Kecepatan gelombangnya 5 meter per sekon itu termasuk tinggi. Ya. Jadi ini didapatkan seperti ini. Ini udah ya, jelas ya. Kemudian ini adalah perbandingan antara gelombang bunyi dengan cahaya itu gimana? Ya, misalkan keduanya itu punya panjang gelombang yang sama, tapi kecepatannya berbeda. Nah, perbandingan antara frekuensi cahaya dengan frekuensi bumi itu 1 jutanya. Jadi bagaimana frekuensi tersebut? Kalau frekuensi pada bunyi yang panjang gelombangnya 3 meter itu 100 Hz. Itu di bawah gelombang yang manusia bisa bunyi. Tidak terdengar. Kalau gelombang cahaya yaitu 100 MHz itu gelombang radio FM. Oke, nah ini terakhir terkait dengan vibrasi ya. Jadi kalau Anda memanaskan makanan di oven yang microwave ya, prinsipnya itu alat tersebut itu menghasilkan microwave yang energinya itu terpusat di pusat makanan. Oke. Sehingga kalau Anda lihat di sana, itu kalau di microwave itu yang panas itu bukan permukaannya dulu, tapi tengah-tengahnya, di dalamnya. Karena seperti tadi prinsipnya. Jadi ini misalkan microwave tersebut menghasilkan panjang gelombang 3 cm. Jadi kita bisa dapatkan frekuensinya 10 GHz. 10 GHz itu artinya apa? Itu adalah 10⁻10 getaran molekul per detik. Jadi molekul itu bergetar secepat ini sangat cepat. Sampai kelajuannya kan sama dengan kelajuan cahaya. Gitu. Nah, ini gambaran grafik antara koefisien penyerapan dari air ya sebagai fungsi dan frekuensi. Jadi kalau frekuensinya tinggi, makin lama-kelamaan dia akan naik, tapi ketika dia itu pada ini tertentu, dia jadi turun. Gitu ya. Yang di kita tidak microwave itu di sini, diserap bisa dipanaskan. Tapi sayangnya kalau untuk gelombang cahaya tampak yang visible, itu di sini, di mana dia lagi turun koefisien absorpsinya. Gitu. Jadi tidak efektif juga seperti itu. Jadi kalau harus efektif. Ini juga salah satu sifat anomali air ya, yang ini sebetulnya namanya water hole. Kemudian ada fungsi gelombang. Fungsi gelombang itu adalah fungsi sinusoidal. Kita ambil sederhananya ya. Untuk di kuliah ini semua seperti ini. Jadi YM itu adalah amplitude, KX kurang omega itu adalah fase atau fasa. Oke, terus K itu adalah bilangan gelombang. Dimana K itu adalah 2pi per lambda. Jadi kalau delta X itu dengan lambda, maka fasanya bertambah 2pi. Sedangkan omega itu adalah frekuensi sudut. Jadi omega itu sama dengan 2pi per T. Jadi kalau delta T sama dengan T, itu artinya fasa bertambah sebanyak 2pi. Oke, kalau yang B di sini itu adalah kelajuan getar ya, atau kelajuan transversal. Jadi arahnya kemana ya? Ke suhu Z gitu, arah getar lah ya gitu. Ada pertanyaan nggak sejauh ini?
Enggak, Pak.
Enggak, oke. Cukup jelas ya rasanya. Ini contoh. Jadi secara umum, gelombang itu secara umum tidak sinusoidal, tapi lebih kompleks gitu ya. Nah, tapi untungnya sekompleks apapun gelombang itu bisa kita disebut kita dapat menggunakan deret Fouillé gitu ya. Untuk menggambarkan ini contohnya adalah gelombang kotak di sini, satu kotak maksimum, satu minimum kotak yang negatif gitu, satu positif, satu negatif. Itu bisa didekati dengan deret Fouillé ya, atau Fouillé series seperti ini. Kemudian ini adalah gelombang yang Y sama dengan min X misalkan ya, pada batas tertentu itu bisa didekati juga dengan deret Fouillé gitu ya. Kemudian ada gelombang sin ya. Kemudian ada lagi seberapa cepat gelombang menjalar, misalkan ya, ini adalah Y, T itu adalah si YM sin KX orang omega T. Jadi kalau dia itu yang atas ini, kalau V-nya lebih besar dari 0, dia dari kiri ke kanan. Kalau lebih kecil dari 0, itu dia ke kiri. Oke. Di mana V di sini adalah sama dengan dx dt sama dengan omega per K. Kemudian yang terakhir bahwa laju gelombang itu hanya bergantung pada mediumnya ya. Medium gitu. Jadi di sini medium itu bekerja antara ada gaya, ada rapat massa gitu. Jadi V di sini dia bergantung pada F dan mu yang merupakan rapat massa dari tali. Ya mungkin itu aja dari saya. Ada pertanyaan nggak? Ada pertanyaan? Kalau tidak ada, saya akhiri ya. Terima kasih semua. Selamat siang. Jaga kesehatan.